We're going to do part 3 of chapter 11 on alcohols and ethers. We're going to do the synthesis and reaction of ethers, including epoxies. Okay, so we've learned that we can take an alcohol here and dehydrate it to make an alkene. But we can also do it at a slightly lower temperature. Instead of losing water, we're going to use one equivalent of water, but we're going to make an ether. Okay, so this is one way to make an ether here. And so what we're going to be doing is we're going to be protonating our alcohol here. And when we do that, we can protonate that alcohol, making that OH a better leaving group, making it neutral water. But we still have an excess of the other alcohol available to us that can act as a nucleophile. It's a poor nucleophile, but it is a nucleophile. And so when it does react, it'll actually form this ether, which is actually can be deprotonated to give us our regular ether. Notice all of these steps are reversible. So you want to do just a little bit of acid and a lot of the alcohol with a little bit of heat. Okay. Now, again, if you heat it too much, it's going to lose water and you'll do that. So we want to look at that. Now, this is a really good way to make symmetrical ethers because you don't know which alcohol is going to be protonated and which alcohol is going to act as the nucleophile. So if you had two different alcohols, you're going to get a mixture. You're going to get alcohol 1 plus alcohol 2, alcohol 1 plus alcohol 1, and alcohol 2 plus alcohol 2. So you're going to get a very bad mixture. So you only want to make symmetrical ethers that way. So if that's so hard to make unsymmetrical ethers this way, is there a good way to make unsymmetrical ethers? And yes, there is. We're going to use another trick called the Williamson ether synthesis. Okay? Now, because the reaction is an SN2 reaction, we have to be very careful about which alkyl halide we use. It's limited only to primaries and some secondaries, those that aren't very hindered, okay? But the alcohol can be primary, secondary, or tertiary in this reaction. So you have to be very selective about which one you want to use. The less substituted side has to be your alkyl halide. The more substituted side has to be your alcohol. Okay, so let's look at that in more detail here. So in the case of this right here, we have a secondary alcohol on this side, and we're going to react it with a primary alkyl halide on this side. The problem is if we swap that right here, we might actually use this as have our elimination as a base, creating an alkene instead. So we want to avoid that. So we're going to use the primary alkyl halide to give us our desired product. Okay, so what we're going to do is we're going to use a base, and in this case we're going to use sodium hydride right here. And so the benefit of sodium hydride is it's not a reversible base. Notice there's no equilibrium here. We're going to generate our nucleophile and hydrogen gas, and that's going to bubble out of the reaction. So we won't have to worry about that. So now we have a good nucleophile and we have a primary substrate. So we're going to do our SN2 reaction to give us our isopropyl ethyl ether. Okay, so that's the key to the Williamson synthesis is you can choose your nucleophile and you can choose your alkyl halide and you get your unsymmetrical ether with no rearrangement. Okay, another example of that is what if you had an alcohol and an alkyl halide on the same substrate? Well, if it can make a 3, 4, 5, 6, maybe even 7-membered ring, it will, because that's a fairly fast reaction. So in this case here, we can use base and just sodium hydroxide. That's enough to deprotonate this just a little bit. And then once you deprotonate a little bit of this, it acts as the nucleophile and it closes the ring and gives us a 5-membered ring. Remember, because it's an intramolecular interaction, that works about 55,000 times faster than an intermolecular reaction because you don't have to diffuse over and find the other product. You're already there and you're just wiggling around in your solvent. Okay, so that makes it really easy to make rings with the Williamson ether synthesis too. So one of the rings that you can make with the Williamson ether synthesis is the epoxy or the oxocyclopropane. Now, the limitation is that your alcohol and your alkyl halide have to be anti to each other or have to be trans to each other. Okay, so for an example in this right here, in this ring, they have to be trans because our nucleophile has to be substituting an SN2. The nucleophile has to come in at 180 degrees from our leaving group. So if we have in this case our trans iodo alcohol cyclohexane right here, we can form the epoxy. However, if we had it here, it can't come up to this side and do an SN2 reaction. There's no SN2 reaction possible. Therefore, we have no reaction possible. We're not going to form any epoxide, and we're probably just going to end up giving us an alkene. Okay, so the Williamson ether synthesis only goes through SN2 mechanisms, and so you have to make sure you have that SN2 available to you. Okay, so there's some other ether synthesis we've already looked at chapter 8. In the oxymercurization, demercurization, if you use alcohol instead of water, you will make an ether, and you'll make that ether at the more substituted side because the mercury stays on the less substituted side until you reduce it off. Okay. Now, you can also make ethers in the acid catalyzed hydration reaction if instead of using water, you use an alcohol. And again, you'll probably make the more substituted version, or it might even rearrange from a secondary to a tertiary because you're going through a carbocation intermediate. Again, these are reviews, so go back to chapter 8 and remember that these exist as ether synthesis. Okay, now let's say you wanted to do a reaction, but the OH is a protic system and therefore would react with some things, okay? So what we're going to do is we're going to do what we call a protection, deprotection systems to make the alcohol not react with something during one reaction, but then we can clip off our protecting group and get it back to do a separate reaction, okay? So in this case here, we're going to protect it as an ether. Ethers have very low reactivity. Alcohols have very high reactivity. So if we convert our alcohol to an ether, then we can make it low reactivity and we can use it to do other reactions. So in this case here, what we're going to do is we're going to use our alcohol, when we're going to use isobutylene and acid catalyst. So the acid catalyst is going to let us make this T-butyl group. All right, so, and obviously it's probably going to be a reaction where we form a carbocation, then this acts as a nucleophile and regenerates our acid to give us our ether. So now we have that ROR group, which is very low reactivity. Okay, so why would we want to do that? Well, let's say we wanted to use something like this. We wanted to make this vinyl group on the end of an alcohol. We had an alkyl bromide with an alcohol on it, and we wanted to use this strong base. Okay, so this has a negative ion here, so that means it's an alkene base, and therefore what would happen is we would actually react with the OH group instead because that's less basic than the alkene base that we just formed here. So what we'd see is instead of having it react as a nucleophile, it's just going to deprotonate this side and end up with undesired products of a salt of our alcohol and ethylene, and that would boil out of the reaction. Okay, so that's not going to give us the product we want. But if we protect that alcohol with that T-butyl group right here by taking our material, reacting with acid and isobutylene, that's going to give us a protected alcohol. So there's no OH. Now, our base here can act as a nucleophile, and ethers are not very susceptible to reactions with nucleophiles. So the ether reacts with the bromide in an SN2 type reaction. And then when we work the reaction up, we can add a little acid, and that clips off the isobutylene, regenerating our alcohol. So we call this protection, deprotection group. And the whole thing we're doing is just removing that really reactive hydrogen, turning it into a less reactive ether, doing chemistry with strong bases, and then clipping it off with acid again. Now, is that the only kind of ether we can use to protect? No, it actually turns out we can use silicon to form silyl ethers to do the same thing. Okay, so in the case of this, we can protect our alcohol using a silyl chloride. So notice there's one chlorine on this and 3 alkyl groups. Okay, so that's going to make a nice strong SiO bond here. Okay, so that makes it an ether. Okay, so that means it's very low reactivity and we can use it to protect it against other nucleophilic attacks, right? So that side won't react with nucleophiles. So then the cool thing about the silyl ether is it's very susceptible to fluoride ion. Just a little bit of fluoride ion in a couple minutes, the whole thing breaks apart because of the very strong silicon-fluorine bond, and we end up generating our hydrogen here. You probably add a little water to the system, and that's where the proton comes from. And then that can be done. Or you can even use HF if you want. However, the tetrabutyl ammonium fluoride is a lot less troublesome to deal with. Okay, so this is a great way to protect things as well. And when you protect it, you can do it with this OTBS, do any kind of nucleophilic substitution you want to do, and then add a fluorine at the end and clip it off and get your alcohol back. Okay, so how would we use this in a system? Well, again, we want to think about our nucleophilic attack here. And in this case here, we're using the acetylide anion as our nucleophile. And our acetylide anion, remember, if we look at our acidity of the acetylene versus the acidity of an alcohol, this is less acidic than this. That means that this is going to protonate this if we put them both in the same reaction at the same time. So what that means is we cannot use this stronger base as a nucleophile in the presence of the OH. So what we're going to do is we're going to protect it with our, we can't use it for that because it's not going to form. It's going to react with this side, and in this case, it's actually going to form THF, a product we don't want. So what we're going to do is we're going to protect it with our silyl group here. We're going to add our TBS chloride to give us our TBSO. That doesn't react with nucleophiles. Now we're going to hit it with a nucleophile, and only the iodine side is going to react. And when we do that, it'll kick out, and then we'll get our reaction to form, add our fluoride ion, that'll clip off that and give us our alcohol back. Okay, so this is what we call protection, deprotection with a silyl ether, a silicon ether. Okay, so let's talk about reaction of ether. I said they have very low reactivity, but they do react with very strong acids, especially with lots of heat. So if you have HBr and HI, you can actually react it with two equivalents of HBr, HI, and it'll actually break them apart. So the first step, of course, is going to be protonation to give us this oxonium cation. And then what can happen is you can cleave the ether by having that oxonium anion form and then having bromide as a nucleophile. Okay, so in this case here, what the mechanism shows is that we have our lone pairs reaching out and grabbing that proton to give us our protonated ether, generating our bromide as a nucleophile. So in this case here, it'll react as a nucleophile and kick out our alcohol and an alkyl halide. Now, again, your slides are wrong, so I've corrected the slide. This is the correct version of the slide right here. We now have our protonated alcohol from here by reacting with another equivalent of HBr. Then our bromine acts as our nucleophile and displaces neutral water and gives us our second equivalent of HBr. So this is our first one. This is our second one. This was our first equivalent of HBr. This is our second equivalent of HBr. Okay, so it takes two equivalents of HBr to break an ether down to two alkyl halides. Okay, so now let's talk about the epoxies, okay? That's the last thing we want to talk about because they have unique reactivity, and it's kind of a cool thing because we can control the way it opens. It can open one way or the other way, and we've already figured out one of the synthesis is we can use the Williamson ether synthesis to make it, but we can also make it from alkenes, okay? The way we make it from alkenes is we use a peroxy acid, okay? So we can use something like peracetic acid, or this is the most common one right here, the MCPBA, or metachloroperoxybenzoic acid, peroxybenzoic acid. So what we have here is basically, imagine a carboxylic acid with an extra oxygen in it. Excuse me. So we have a carboxylic acid with an extra oxygen in it. Okay. So how does that work? Well, it's really cool reaction. It's kind of a concerted thing, just like when we're forming that little circular. Okay, so how do these peracetic acids work? Well, it turns out we form a nice little intermediate with our alkene, just like when we reacted bromine, but in the case of this, we have this oxygen here is actually partially positive. It's making it an electrophile. These have extra electrons, making it a nucleophile. And so in the case here, the electrons from the alkene reach out to the oxygen, electrons from the oxygen reach out to the other carbon of the alkene, in a concerted reaction, so it happens all at once. Now notice what happens up here with the acid. We're transferring the hydrogen from the acid portion to the carbonyl side of the carboxylic acid, and we're generating the carbonyl on the other side of the bond. So we have nice carboxylic acid as a leaving group in our epoxide form, okay? So any per acid will create our epoxy from our alkenes. Okay, but now there is some stereochemistry. Because we're adding syn addition, right, we have to think about how the products are going to show up. So we have a trans alkene here, okay, which means in our product, because we have a ring now, okay, we have cis and trans isomerization in our rings. And so because we have a ring, we're going to end up making the trans ring. Notice they're on opposite sides of the ring from each other. Now, if we start with a cis alkene, we're going to end up with a trans ring, a cis ring too. So we're going to end up with a cis alkene turning into a cis ring system, a trans alkene turning into a trans ring system. Okay. All right. So those are those correctly stated. Okay. Now let's talk about the reaction. Because this is a strained ring, right? The cyclopropane was a strained ring. Well, this is a strained ring too. It makes it want to open up much, and it's much more reactive than any other ether. Okay. So it's susceptible to nucleophilic substitution. Okay, but two things can happen. If it's acid catalyzed, the nucleophile opens it at the more substituted carbon. If it's base catalyzed, it opens it at the less substituted carbon. So what does that mean? Well, okay, let's look at the acid-based first, okay? So in the case of the acid-base, we still have two lone pairs on the oxygen. And what that gives us is it is a Lewis base. And so we can actually have it protonated. Now, when we have it protonated here, we can have attack of the nucleophile at either carbon, but the nucleophile is going to attack at the more substituted carbon because it's going to have more of the partially positive charge. Now, the first thing to note here is that we are always going to have anti-addition. We are always going to have anti-addition because the three-membered ring blocks one side of it. The the water is going to come in from the other side of it. So notice this is a good way to make diols, 1,2 diols. Okay. So that being said, let's look at our system here. We will always have in an acid catalyzed system our nucleophile attack at the more substituted carbon. Now, if we attack with water, we really can't tell which one is. So what we're going to do is we're going to attack it with an alcohol instead to form an ether on the substituted side, and the OH on the side that opened up. So that was the oxygen from the epoxy. So if we use this acid catalyzed system with this as our nucleophile here, we always have our methyl, our attack of the nucleophile on the more substituted carbon. So if we're thinking about why that is, well, if we have this ring and it gets protonated, it's going to want to strain a little bit, and it's going to want a more partially positive charge on the more substituted carbon. That makes that side of the oxycyclopropane more reactive to nucleophiles because it has more of a partially positive charge. Therefore, our methanol is going to attack that side, and again, it'll start protonated, and then, of course, it'll lose that proton to whatever the acid is. That's why it's acid catalyzed ring opening. But notice we followed it. It's not a diol anymore. We can actually say the methanol attacked the more substituted side with an acid catalyst. Okay. Now, let's look at that. That gives us an opportunity for trans 1,2 diols. Okay, because it's an anti-addition, it gives us a trans. But we really can't see it that well on where we have the free rotation here. So if we do it such that we have our free rotation, we remove that free rotation, we can see that we can get a difference. We already found out we can make cis diols. This is the cis 1,2 diol by using reactions that form a syn addition on there, the cold potassium permanganate and the cold osmium tetroxide. That gives us our 1,2 cis diols. But with using our epoxidizing agent, we can make our epoxy here first. Then we have acid to catalyze it. Water attacks anti, giving us our trans diol. Okay, so now we have a new reaction. okay? Because we had cis diols before, now we have a new way to make trans diols. Okay, all right, in the base catalyzed reaction, we're going to see the opposite effect, okay? Instead of having the nucleophile attack at the more substituted side, we're going to actually have the nucleophile attack at the less substituted side. Think about that. In SN2 reactions, they attack primaries and some secondaries, and methyl groups better. So let's look at that system, okay? In the case of the epoxy, because it's like an SN1 reaction, it is going to open the ring from the less substituted side, the less hindered side. So again, if we used water, we wouldn't be able to see which side is which. But if we use alcohol as our nucleophile, and notice this is not just the alcohol, this is the alkoxide. So we've deprotonated the alcohol, making it a base. Okay, so if it's the base, it's going to attack the less substituted side because this is sterically hindered. So we have to attack the less substituted side, giving us the thing. It's still an anti-addition, so it's still an anti-addition, but it attacks the less substituted side. All right, so let's review everything we know about alcohols and ethers to close out this chapter. Okay, so now we have synthesis of primary alcohols. We can make primary alcohols by attacking an epoxy with a base, and that'll ring open to give us a primary alcohol. We can take a primary alkyl halide, displace it with hydroxide in an SN2 reaction. So this is an SN2, this is an SN2, and then this, of course, is a syn addition, a boronation oxidation reaction. So that's to make a primary alcohol. And you might want to separate this out on your reaction table to say these make primary alcohols. Okay, but if we want to make a secondary alcohol, we have a couple ways to do that. We can hydrolyze this if there's no chance for a tertiary carbocation. We can use mercurization, demercurization, or we can use hydroboration of an internal alkene, which will give us a secondary alcohol. Remember, if we use a terminal or an internal alkene with oxymercurization, it'll always give us a secondary alcohol. And when we use a alkene, it'll always give us a secondary or tertiary alcohol. All right, so in review also, we can take our alkyl halide and turn it into carbocation and then turn it into an alcohol through hydration. We can take our alkene, and if it can make a tertiary carbocation, it will, and we can get a tertiary alcohol. And if we have a unsymmetrically substituted alkene, such that it's substituted twice, we're going to get anti-addition, and the mercury is going to be on the outside, meaning our OH is going to be at the tertiary position. So we get a tertiary alcohol. Okay, so those are very selective, right? Primary alcohol, 3 reactions. Secondary alcohol, 3 reactions. Tertiary alcohol, 3 reactions. So these should all be separate lines on your reaction table. All right, so what can alcohols do? Well, we can convert alcohols into ethers by using the Williamson ether synthesis. We can dehydrate it to make alkenes using acid-catalyzed dehydration. We can turn it into a better leaving group with the tosyl group, the mesylate group, or the triflate group, right? That turns it into a good leaving group as well. We can convert it to primary alkyl halides, like the chloride with thionyl chloride, the bromide with PBr3, and we can create some of the other ones, like the iodine version, using acid. Okay. Now let's talk about ether synthesis. We have the primary ether synthesis is going to be our Williamson ether synthesis, or our symmetrical ether synthesis with acid and lower heat. Okay. Then the only thing we really can do with them is we can cleave them with 2 equivalents of our acid to generate 2 equivalents of our alkyl halide, or 1 equivalent of the alcohol. Okay, so that is all the reactions that we've learned in those last few chapters, and notice how they relate to each other in the fact that we can make primaries, secondaries, tertiaries, we can make ethers, we can make protected ethers, we can make ethers that are better leaving groups by turning them to sulfonyl compounds, the triflate, the mesylate, and the tosylate. All right, that's the end of chapter 11